this webinar, and then we will be taking your questions later on in the session. So welcome all, and hopefully you find this very informative and educational session, and we look forward very much to all of your questions.
Thank you, Robin, for the introduction. I am Caroline Foresti here in France. I'll be presenting you the new model, the liquefaction model of WebSprint application. I'll just share my screen so you can see my presentation. So, here you have my presentation normally. Just let me know if you're not seeing it well. So, okay. We will just start. So as I said, my name is Caroline Foresti. I work here in Soil Solutions. Sorry. Yes, that's perfect. So you see my screen well? Can you just tell me?
Yes, it's okay.
Okay. So I'm Caroline Foresti. I work here in Soil Solutions. So Soil Solutions, it's a French company that develop equipment and also software. Today I'll be presenting a webinar on liquefaction risk evaluation. It's around the liquefaction model we have here. That is inside the application, WebSprint application. I'll be talking about the application itself if you don't know it. So the idea here is not to be doing a class on liquefaction, as Robin said. It's only to present fastly the model, so you can use it to your calculation of liquefaction risk. So the presentation I'll be showing today, I divide in a couple of topics. First of all, I'll introduce you to the WebSprint application. For those who are not familiar with, I mean, inside this application, you can do other type of calculations. Today we'll be talking about liquefaction, but you can also do compaction control and soil investigation and so on. And then I'll be recalling some important aspects of liquefaction, soil liquefaction, the minimal aspects and key basic information so you can apply this calculation model. And then I'll present the liquefaction model itself. Then we'll be doing an example with some data we got here in France in the port of Sète, south of France. We have some data on this site, and then we can apply different methods of liquefaction to evaluate liquefaction. And then, as Robin said, actually in the end, I'll give you a couple minutes so we can try to answer your questions. So I'll just ask you if you can write your questions down in the chat, and later on we'll try to answer them. WebSprint platform, WebSprint application. What is it exactly? Actually, it's a cloud-based platform that allows you to manage, interpret, and store your geotechnical data. The idea is that you get your in-situ data from different tools, not only tools of soil solution producers such as Grizzly and Panda, but also other tools, traditional geotechnical tools, to the SPT, CPT, and so on. And you put this data, you can upload this data to DataSprint, because actually the application is divided into two parts, DataSprint and MindSprint. So you upload your data to DataSprint, you can visualize it, you can rename it, you can do different things, manage it, and then you can apply it to your projects inside MindSprint. Because actually MindSprint will have different models, compaction control that will apply French standard, use data from Grizzly and Panda, applying French standard, and then allow you to do compaction control, and then soil investigation also, some correlation, plate load test, and then liquefaction, the one we'll be talking about today, and also this new model on shallow foundation to design your foundations and verify your foundations. So inside this platform, as I said, we have this liquefaction model, the one we'll be talking about today. To apply this model, I think it's important to talk about what kind of liquefaction this model will be dealing with, because actually there are different kinds of instabilities that can occur in soil. And there are some instabilities such that are not, we cannot use this model to calculate, to verify this kind of instability. Actually, liquefaction model of WebSprint will be dealing only with cyclical liquefaction, usually called true liquefaction. They occur in loose and very loose saturated non-cohesive soils. Actually, I think it's important to say that because we have other phenomena such as cyclic mobility and other instabilities that can occur in clay soils, this kind of instability is not taken into account in this model. So you can't use the liquefaction model to deal with this. But with, I would say, true liquefaction, cyclical liquefaction, will be the one we'll be dealing with here. So, as I said, it concerns loose, very loose, saturated, no cohesive soils, subjected to cyclic shear on drain conditions. So actually, earthquake and this kind of solicitation that we will increase pore pressure, and then with pore pressure, we will eventually reach confining pressure, which will cause a loss of strength, and then cause also larger strains. Soil will experience large strains actually, and this is the kind of phenomenon, this type of phenomenon that we'll be dealing with here. Actually, this is a phenomenon considered a shallow soil phenomenon that will occur mostly in soil under low confining pressure, so under 40 kilopascal, and so around 15 meters also. We usually say no more than 20 meters depth. So to deal with this kind of liquefaction, this true liquefaction, we have this different methods to assess risk, to quantify this risk. Usually the initial methods were based on laboratory tests, and then later on we had some these empirical methods that arose based on in situ tests. To start, it was SPT and then CPT. Today we have methods based on shear wave velocity, and we also have methods developed by Soil Solution based on dynamic penetrometer data. So this is the one implemented in a model, in a liquefaction model of WebSprint. So this is the one you can apply with this platform. And also we have nowadays numerical modeling, which are not implemented in WebSprint. So actually what this liquefaction model will be applying is the simplified procedure, which is international reference based on Wood and Idris, the work of Yudi and Idris, that will propose a factor of security. This factor of security is based on a ratio between cyclic resistance ratio that will be determined from mechanical results in situ. In this method, it will use data from mechanical data from in situ tests, different data, SPT, CPT, dynamic tests, and so on. Normalized to the moment magnitude of 7.5, and then we have this term will be divided by the cyclic shear ratio that will account for the solicitation induced by earthquake. Actually, you will need for your calculation to have the acceleration caused by the earthquake divided by acceleration, gravity. Divided by gravity, and then you have some stress information, initial stress information, and effective stress also. And this term that will take into account the fact that the soil column is not rigid. So it will correct this effect. And then we also have a magnitude scaling factor that will allow you to correct these terms, so it will compare them to moment magnitude of 7.5. Actually, will compensate for the fact that the magnitude you have in situ is not exactly 7.5. And then you have other coefficients that can be applied to correct for stress, confining pressure, for greater depths, that is K sigma, and then we have K alpha that will take into account for the slope of the in situ slope that actually will be not taken into account in this model. Actually, it's this correction factor. It's not. We don't have a consensus in the literature nowadays, so it's complicated to apply it. So we take it equals to 1 in the case of liquefaction model. So this is I'm just recalling it. I suppose you did already, but actually we'll be applying exactly this formula for a different calculation in WebSprint. And actually this formula came from some institute observation when they realized that when comparing normalized resistance parameters here using parameters from SPT, correct with different, of course, applying different corrections in terms of the energy, in terms of atmosphere. So it will take into account only one atmosphere and so on. What they realize actually that we have this different areas. We can establish different areas where liquefaction occur when a liquefaction didn't occur. So in this can be observed with different in situ data. So data from SPT, CPT, and shear wave velocity, or classically, in more classical way. And actually we can observe that with dynamic tests also. So we can apply the same idea to dynamic test results. Actually, inside WebSprint, it's important to recall, actually, we can also do an evaluation of liquefaction consequences. Not all liquefaction softwares allowed to do this kind of estimation, so I think it's important to talk about it. What WebSprint will be doing is actually will be applying the work of Ishira and Yoshimine. Actually, we have this family. They propose this family of relationships that allow to estimate volumetric strain for saturated layers where liquefaction occur. So from a factor of safety that will be determined anyways when applying the simplified procedure. We can also from soil parameters actually relative density of soil, or parameters from SPT or CPT resistance parameters. We can also estimate the volumetric strain and doing some hypotheses, apply some hypotheses to simplify the problem, the system. We can also estimate the sediments caused by liquefaction, so for saturated layers. So WebSprint will be also showing this sediments, the estimation of the sediments caused by the earthquake, by the solicitation. So this will be doing by applying 2 different correlations to estimate parameters or parameters that will be used to apply these correlations proposed by Ishara. These are the ones we'll be applying in the software from Idris and Boulanger or from Zan and Robertson. So you can choose inside the platform which one you prefer. And also complement another parameter, another thing that we can use to to give you more information about your evaluation of liquefaction is to determine the liquefaction potential index. It's something that not only I always say that we can do this with the PLUS platform, because not all software are allowed to do this kind of estimation. But actually, what I imagine you already know it, but actually it allows you to give you a global parameter characterizing the entire soil column, because when we apply the simplified procedure I told you about, we will be plotting a factor of safety in function of depth. So it's a result that can evolve within depth. And here, the fact of calculating the liquefaction potential index will allow you to give you a overall, let's say, evaluation of liquefaction risk. Actually, we'll be calculating taking into account the factor of safety for depth from 1 to 20 meters depth, and we'll ponderate it to the depth, because actually more you go, more deeper you are, less chance of having liquefaction you have. So we will ponderate both factor of safety and the factor and the depth, and we'll give you a total parameter, let's say. And then to evaluate this number you have this classification. Actually, if you have LP between 0 and 2, have low, moderate, and high, and very high expected damage level. So it's also important to give an overall evaluation. So inside the platform, as I said, so this platform is a tool to liquefaction analysis for soil under seismic loading. The idea here is that what will be triggering liquefaction is the seismic loading. It's earthquake stress caused by earthquake, and based on in situ methods. As I said, there are also other methods based on laboratory tests, and these methods are not taken into account here. So inside the platform, the analysis we'll be doing the analysis in different stages. Actually, first of all, we'll be checking for seismic parameters of the site you'll be testing, we'll be evaluating. So this part we call it opportunity normally. So for this analysis, you need the peak ground acceleration and the momentum magnitude called in the site. So you take historical data, and you know what's the kind of earthquake that can occur, the intensity, social elicitation, and so on. And this is important because actually, if you're dealing with a site that's not seismic at all, actually the chances you get in liquefactions are pretty low, or this kind of instability, the chances of getting that, it's pretty low. So actually, this type of sites are sometimes not taking. We don't do this kind of verification. And then other aspect that we'll be checking is the susceptibility that concerns soil parameters. So actually, we'll be doing this analysis based on the laboratory results for each layer. So you need the plasticity index, you need the percentage of clay for that, and of course the fact that the layers is saturated or not. I mean, we're taking into account a couple of aspects to see if the soil is susceptible or not to liquefaction. And then once you see you have the opportunity, you have the solicitation, you have a soil that is susceptible to liquefaction, we'll be doing this quantification of the risk, and then we'll be applying the method that I just showed you, dividing CRR, CSR, and calculate a factor of security in function of versus depth. And for that, you'll be using in situ data for resistance, and then seismic parameters and in situ stress conditions for CSR. And then once we have this evaluation, we'll be doing evaluation of consequences, because now we've verified that liquefaction can occur, and then we'll be just checking how bad it will be. I mean, evaluating how bad the consequences will be. For that, we'll be estimating settlements. As I told you before, we applied different relationships proposed by Ishihara, and then we'll be calculating overall parameter that it's liquefaction potential index. So just to give you an overall idea of the software, so we'll be applying this different stages to, as an example, you'll be using today that data from Port of Sat, as I said, in the south of France. Actually, it's a sandy site, so I mean, it's well adapted for this kind of verification. The idea of this, this example will be applying today, is to quantify liquefaction risk in function of the depth. So we'll be calculating factor of security, and then we'll be evaluating consequences, estimating settlements for saturated layers, and then determine LPI. So we'll be doing that today inside the platform. To give you some information about the site, so the site, as I said, is located in the south of France. Actually, it's an area that has been where they did a backfield of sand backfield of between 4 and 6.5 meters of sand. And then the groundwater table was observed in a depth of 2.4 meters, around 2.4 meters. Here you have image of the site. As I said, in this place, we did a couple of tests. We did some CPT and also Panda tests, some Grizzly tests, SPT, pressure meters, seismic testing, and we got some samples to do some soil characterization also, so we can get input data to our susceptibility analysis. Here you have some photos of the site. And then we have this section where I show you a bit more of this about the site. As I told you, you have a groundwater table at 2.4, around 2.4. Here we have some information about the soil we have there, the percentage of finest content, the fact that actually at the laboratory they verified it's non-plastic soil. And also it's located, actually the site is located in the south of France. Actually, France is not a very seismic country. I mean, not a metropolitan, and France, I mean, some places there are other departments that are not situated in Europe but not France. So actually for this analysis will be this zone, this place, exactly when we did this testing, is classified using Euro code 8 as zone 2. So it's not a seismic area, it's not that seismic, but for the analysis we'll be doing today, we'll be putting it as zone 3 or 4. So you can, so the peak ground acceleration is higher, moment magnitude is higher, and you can have some areas of the site that they will liquefy, so you can see a more interesting result. So let's go directly to the platform. As I said, we're doing this example. Here is the platform I was talking about, WebSprint. I'll maybe put it on the chat so you can see it. So actually, inside this platform, as I said, it's a cloud-based platform. You can work with your colleagues on the same project. You have different languages here. I'm using it in English, of course. You can do a free trial also during the month, so you can test the platform. And inside the platform, we'll be clicking in WebSprint. As I said, inside the WebSprint platform, we have two pods, DataSprint and MindSprint. Today we'll be using MindSprint to do this analysis. I already created a project we'll be working on, so easier. So here we have the example for the port of SAT. So here we have, actually, as I told you, we have inside the platform, you have SPT, CPT, shear velocity, and dynamic test methods implemented. We have these different possibilities. So you can use it with equipment from Solid Solution, dynamic potentiometers, and also with other classical tools. Here, the example we'll be doing today is based on CPT, because actually CPT is a reference tool for this kind of analysis, especially in Europe. So as I show you here, it's the example of results. We'll be doing a different stage so we can get to this result. We have overall result aside. So to start with, how it's done and how we can get these results inside the platform. So the platform is here, you can see it's divided in 4 stages, I'd say. So in the beginning, you'll be given some geography information of the site you'll be analyzing. So here you can import your data. Here we have a couple of data, as I said, to the site. I'll just click on data I want to import. So thanks to the GPS coordinates of this data, you can also visualize the position of the test, as I said, in the south of France. And then you can also enter the coordinates if you don't have the GPS data from the result, the test, directly from the test. And then we can use the Aero Code Assistant here. Aero Code 8 will be applied. As I said, we have this classification of sites, risk associated to site, from very low to high. In the port of SAT, in this region, we'll be analyzing, normally it's low, but for this analysis, I'll be putting it as free. Otherwise, you see that the material not liquefied at all, so not that interesting, I'd say. And then you can take into account some ponderation coefficients that are used in Aero Code recommended by Aero Code 8. So the soil classification, and then the characteristic of importance of the what you will be building in the site. Here it's only parking lot, so I'll be putting 2. And then as you put you enter this input information, it will calculate automatically the maximum acceleration, everything intermediate parameters, so you can get the PGA, peak ground acceleration, and then you can get the moment magnitude, which are the most important parameters in this phase of the analysis. And then once you get these 2 input parameters, but actually here, as I said, we were using this Aero Code Assistant. If you're not using Aero Code, you can also enter a value data from your site. You're not, you don't have to use Aero Code Assistant. Of course, you can enter the moment magnitude and PGA you want. And then you also can choose the magnitude scaling factor. There are different estimations, let's say, ways of correcting this magnitude. There are values that will be overestimating, underestimating, and actually average value. I'll be using an average value. Actually, the models will be applying are different, so you can choose that. And then you'll be giving some important information on site. Actually, water table, groundwater table are pretty important for this analysis. As I said, it's 2.4 meters depth here in this case of this site. Then you give some information so we can evaluate the susceptibility, so percentage of clay. Here we're only dealing with one layer, as I said. Actually, we have one layer. It's a sandy layer. It's a silt and sand we have in this layer. So here you can put the clay content and the plastic index. In the case of this material, it's non-plastic. So 0. We had 0 in a result as a result of laboratory tests. And then you have to import your different layers. Here I'm putting it as a sand. I'm putting the bottom side, bottom depth of the layer, and then saturated density, the density, bulk density. These are information I had already from SIT investigation we did. And then here I will have the result for this layer in terms of susceptibility. And as you see here, this layer is considered susceptible to liquefaction. So because it's considered susceptible to liquefaction, we have to evaluate the risk, quantify this risk. Here, actually, we have the synthesis of the information you just enter, and also you can enter the project water table depth, because actually sometimes groundwater table can change from the moment you did the test, and after all you can put a backfield or an excavation, and depending on what you'll be doing in the case of your project. Here I'm putting a backfield of 1 meter, which is the case for this project. I'm putting the bulk density of this material, of this backfill, and then confirm. And as you can see here, you have 2 profiles: the initial profile with a groundwater table, and then the project profile after the backfill we just did. And then important is to give them mechanical information, so you can calculate the factor of security, as I said previously. We have this different data here we have data from Panda, data from Grizzly, SPT. Here I'll be using, we can use different profiles. You can choose the profile you want to use. We tend to use, the lower resistance profiles, so we can be more safe. Here I'll take any profile. I'm taking this CPT10, for example. Here you can see the results, the profile, so you can visualize it and choose it as you will. And then as I choose CPT10, what we'll be doing next is that we'll be editing calculation settings. I'll be choosing an international reference, as I said, simplified procedure. I can put a target in terms of factor of safety. Here I'm doing the recommendation of Eurocode 8. So I'm taking the value that Eurocode 8 will be recommending. Then we have this, as I told you before, we have 2 implemented correlation methods for liquefaction volumetric strain. I'm using just the first one as an example. And then we have the sigma correction for the tap. Here we'll be dealing with a shallow depth, I would say not that deep depth, so I won't take it into account. Normally, if you're dealing with higher depths, you should take it into account. And you can apply some post-treatment of processing of data. Also, you can apply some regularization, some smoothing, because of the high resolution of this data. We have some outliers sometimes. And then we have the summary of different hypotheses and different things you selected, so you can double check it. And from that the results will be generated. You have this recall in a report file you used, the post-treatment you used, the regularization, and then the calculation of CRR, CSR. Then the ratio between them allow you to deduce the factor of safety. As I said, for this site, we will have the zone. Actually, you see in this factor of safety, there is plot against versus the depth. You see that there's different zones. This part, green part, actually is the superior to the target value of safety, factor of safety. Actually, you have this orange area between the target and 1, and a red zone that's supposed to show you if you have liquefaction occurring, that the factor of security is under 1, which is not the case here, as you see, because actually this site is not that liquefiable. And then we have seismically induced sediments that will be calculated from the shallower depth to the top, and we have in the surface around 8 millimeters. So sediments of 8 millimeters, estimated as 8 millimeters, and liquefiable zones within the depth. And you have this calculation hypothesis you selected before. It recalls all your information, and you see no risk. Actually, as an exercise, I'll just go back to the first part of this analysis, and I'll be putting the site not as moderate, but as average. So I'll taking as an hypothesis that actually it's a site that are more, have some more seismic site. And if you go to results, you can see I'm passing past all the parts because I'm not changing anything else other than the seismicity of the site. And as you can see, we have the same results, except for the fact that actually we have the safety. The factor of security that's pretty, that changed, of course. We have this part of some zones within depth that are now liquefiable. So the factor of security is under 1. And you can see here, when you see the value of liquefaction potential index, that it can be classified as moderate risk. So we have a minimal factor safety that is now lower, induced sediments on the surface for all the layers that are saturated. And then once you got your results, you can also download your results to format. You can download it in Excel data like this. I just downloaded all my data. As you can see here, you have the data you used to your calculation, mechanical data you selected, and then the calculation of CRR and CSR, the factor of security, and then seismically induced settlements, all this information plot versus depth, sorry, and then we have liquefaction limit height, and we have all this information. You can use it, and also you can download your data clicking here as a PDF, the PDF format. Actually, it's a report and will show you all the hypotheses you used and all the correct parameters of soil you used, the methods you used for your calculation, and you give you also the different graphs you got. So it's a report you can generate. So you can generate results in these 2 ways. Here, I just showed you the example with CPT. As I told you, you can do the same with Panda data, Grizzly data, SPT, but because it's a reference tool, I just chose to use a CPT for this analysis. So I'd say that for WebSprint was pretty much it. I will just see if there is any questions about what I presented. So I don't know if it was clear enough. If you have any question, you can also feel free to reach us anytime you want. I'll just show you my mail address again.
I think you can switch on your microphone if you have any question. I think they are open. Or you can use the chat if you want. I think that people are writing, so.
I'm not sure.
Not sure if you can switch on your microphone, but.
I'm not sure. I think we settled it not to. If you have any questions. Oh, so how reliable is Panda for liquefaction assessment? Actually, Panda methods, Panda-based methods that are based on Panda data will rely on correlations between Panda. Usually rely on correlations between Panda and CPT. And actually then the reliability of these methods will depend on reliability also of correlations you will be using. So the method, there are different methods. Actually, there are two main methods that will be applying Panda and Grizzly. One will be using soil permeability and resistance profile, which is Liquefaction method that is implemented. And also there's a method that is more well suited for mining waste material that will be using factor fines content and fines content to deduce bearing behavior soil parameter of Robertson, and also we'll be using relationship between dynamic resistance and cone resistance. So actually the reliability of these methods will mainly depend on reliability of your correlation also between Panda data and CPT data. But actually it's the maximum, when it comes with the maximal investigation depth, will depend also the tool you'll be using. For Panda, actually we recommend until the depth, maximal depth of around 7 to 8 meters. It depends on the soil we'll be testing, actually, of course. And Grizzly, we recommend it to a depth, maximal depth of around 14, 15 meters. As I said, depends on the soil we'll be testing. But anyways, liquefaction phenomenon, it's a shallow depth phenomenon. As I said, the maximum from 15 to 20 meters, let's say the liquefaction risk, it's a bit lower. So shallower depths are the ones that are more susceptible anyways. I don't know if the question was complete. As you can ask other questions. I don't know if it was clear enough. Normally, the liquefaction phenomenon will be, the risk will be higher in the shallower depths. So, anyways, if you have only data from CPT or SPT, you can apply the methods based on CPT or SPT. For CPT, it's the method we just showed. Actually, we won't be using dynamic data. You can, it's all, say, other method that is applied. You can use your data from CPT, and then will be the method from IDRIS that will be applied. Of course, there are some corrections will be required. And then SPT also, I mean, you don't have to have the data from dynamic tests to apply these methods. You can use conversion and input. You can also use, of course, you have some, as I said, inside the WebSprint, you have correlation models that you can apply it also to deduce from your dynamic profile, from your dynamic resistance profile, to estimate your SPT or your CPT profile. Depends on the soil you'll be using, of course. But you are not, it's not mandatory. I mean, you can use your data from SPT and apply IDRIS method, and CPT applies Robertson method, and not have any dynamic soil and dynamic resistance data.
Any more questions for Caroline?
I mean, I didn't talk about it that much, but it's the same for shear velocity also. We'll be applying Andrew's method, and it doesn't require any information on dynamic resistance. It's the same, only with your information from soil, of course, results from data from laboratory tests, and shear velocity profile. You can apply Andrew's method without using any dynamic resistance, of course.
Perfect. Caroline, did you by any chance do work in your PhD on this topic?
Not at all. Actually, I was working with a new prototype of a new equipment we're developing. Actually, it's a new version of Panda 3 with accelerometer, so nothing related to this. So I mean, I'm trying to understand a bit more. As I said, getting as much as information as I can, and
sure,
was happy sharing with you. Anyways.
Any more questions for Caroline before we close off today? Okay, well, let's call it there. Caroline, Clément, thank you both very much indeed for putting on today's session. Hopefully everybody found it useful and educational. And if you want to find out more about the module, then feel free to reach out to us, and either In Situ Tech or Source Solution, and we'll do our best to serve you guys, answer any questions that you might have, and so on as well. Thank you all very much indeed for coming along. Really appreciate your attendance, and enjoy the rest of your day.
Thank you, everyone.
Thank you very much, Robin. Normally, the link for downloading the video will be available in the chat. If not, I will send it to you, or Robin will do it. Let's see how we can, how we will do it.
Thank you, everyone.
Thank you all very much.
Thank you very much.
Sure.
Bye.
Bye.